Welcome to Talkcast and to Science News number 2. I did one of these a few months ago. It was focused on a single topic, population 3 stars. Scroll back through my videos on my podcast to find that. This one is going to be a little more diverse, although still with a physics astronomy type focus. There's a lot of people out there doing science type news these days, but to my mind, no matter how expert the presenter, they might be ex-physicists or even existing professors, professional scientists, very few seem all that concerned about epistemology, which means they're either too credulous, which means too ready to believe the latest claim to come out of a lab to be actually true, or, at the other extreme, they're too skeptical, wedded to some already existing hypothesis of theirs and unable to accept reality because, well, they just can't believe it. It's all couched in terms of what they can and can't believe. And that's no standard for knowledge. It's certainly no standard for science. There's the modern equivalent of those who believed Pons and Fleischmann in 1989 had achieved room temperature fusion in their lab, or perhaps today, endorsed those reports of government employees whose testimony attests to the housing of alien spacecraft and indeed specimens of alien life the US military has in certain installations. So you've got that at one end, the people who are credulous and believing, and at the other end, those who still say, for example, quantum computers will never be possible, or we didn't go to the moon. These are all extreme versions of the same error. That the strength of your personal conviction in matters of science is what determines, or has some bearing upon, whether or not some theory actually explains what is going on or not. The alternative is whether we should wait for the crucial evidence to be collected or the crucial proof to be demonstrated. But, not every failure of human thinking on these topics, mistakes and errors, in other words, are quite of the magnitude of those I've just mentioned. Some are more subtle, but it's always and everywhere a consequence of the wrong epistemology. Thinking either that accumulating more evidence will make you more confident, or should increase your confidence, or that reality must conform to your own pre-existing prejudices, even if you call that prejudice common sense. So here with Talkcast Science News, for want of another title for these sporadic, episodic chapters, we try to set the record straight with what we know, what's a problem, and what the purpose of evidence is. As I like to say, scientists, even professional ones, no more need to understand the intricate details of the process by which science creates knowledge, the function of evidence, let's say, then the pilot needs to understand precisely how the jet engines work. All scientists agree that evidence is required, well, at least most of them do most of the time, modulo certain theoretical physicists working in some areas. But most scientists don't need to know the precise details of how the evidence works, what the function of it is, although they should, any more than a pilot needs to understand exactly how jet engines work. It'd be preferable if your pilot knew precisely how the jet engines work and how the scientists, and if scientists knew precisely what the function of evidence was. But reality is, they don't. Most pilots might have spent years getting up their flying hours and studying theoretical aspects of jet engines, but they're rarely getting their hands greasy with oil as they tighten screws on the turbines. We're looking at whether or not there are screws on these turbines, so to speak, and how loose they are. That's our purpose here with this science news. We want to know whether or not the plane's able to fly. Emblematic of all this is going to be my news item number 1. It's been a perennial source of headlines and hot takes for decades now. Dark matter. So let's get into it. Well, first, let's recall a little bit of background. Dark matter is the name of a problem, not a solution. It's not a theory or an explanation. Certainly not a good explanation in Deutsch's sense, the Popperian worldview. It's an easy-to-vary hypothesis by which I mean, well, there are lots of different models of dark matter that might fill the bill, and none of them so far have actually been able to solve the problem that we have, and so it's just called dark matter to label a problem. The first of these problems that arose that caused people to go, aha, dark matter, were observations of the rotation of spiral galaxies. They were rotating too fast. You can measure the rate of rotation of a galaxy when they are aligned just so, in the right way, with Earth, when you're observing them through telescopes and using spectroscopes, so that when you see them at just the right angle, you can measure the redshift of the side of the galaxy that's receding from you, it's moving away from you, and against the other side of the galaxy, which is comparatively moving towards you. It has a, relatively speaking, blue shift. And that tells you the rate of rotation. Red shift in one direction, blue shift in the other direction. Take account of those, and you can see how fast the thing is spinning. And what's been found systematically, in other words, in all galaxies that have been studied, was that they're rotating too fast. Then when you try to apply regular theories of gravity to those galaxies, they make a prediction. Given the amount of mass in the galaxy, how fast should the objects in that galaxy be moving? More massive systems rotate faster. The Earth goes around the Sun as fast as it does because of the mass of the Sun. At least 99.999% of the explanation as to why the Earth travels as fast as it does, why it takes 365 days, no more, no less, to go around the Sun is because of the mass of the Sun. If you increased the mass of the Sun, then the year would get shorter and shorter. So instead of 365 days, you'd have 360 days, 200 days, 100 days. Name your number, there would be a mass of the Sun that would determine the rate at which the Earth orbited it at this particular distance, 150 million kilometres from the Sun. This is also, by the way, if you replace the Sun as, the all-powerful oracle or god or simulator, whatever you want, if you were to replace our Sun with a black hole of the same mass as the Sun, we would not get sucked in. That's a common misconception. We'd just continue happily orbiting the Sun at the same distance forevermore. Perhaps not happily, because we'd be gradually, or rather rapidly, freezing to death. Because unless we figure out a way to harness the geothermal energy from the core of the Earth long enough to get us off this planet, well, we'd be stuck here until the last of us freeze to death. There's a science fiction plotline for you. You're welcome. So, news right now with respect to all of this stuff, dark matter I should say, is that there have been binary stars recently observed. Here's the paper. They seem to be orbiting in a way, so it is said, consistent, not with the prevailing view of gravity, general relativity, but rather with MOND, M-O-N-D, modified Newtonian dynamics. This is a theory, I say theory in scare quotes, that has been around for decades now. I had a look into it when I was at university. It crops up now and again. It is an instrumentalist idea. The thing is, thousands of astronomers are at work every day publishing observations of all manner of things. Astronomy is hard, not least because although we get better and better all the time at making precision measurements, we're still looking at the most distant objects imaginable with tools that have tolerances, telescopes with a limit of reading and spectroscopes with errors associated, and people interpreting all of this stuff. Here's a possibility regarding this particular claim that this binary system is consistent with modified Newtonian dynamics. It is for now, let's just say, a theory that is different to Newton's theory of gravity, different to the theory of general relativity, and it's just an equation that predicts how planets orbit the Sun, or in particular, how galaxies rotate is the most important thing. Anyway, this paper says that the observations of this binary system are consistent with MOND, consistent with the equation that predicts the movement of these objects when they're orbiting each other. Well, consistent with says nothing about the truth or otherwise of that theory, of course. It could be experimental error due to instrumentation calibration, or plain old scientific error by a scientist. This is a single author, after all. But some popularisers are making a big deal about this rather minor study. Some popularisers who, let's say, might have a barrow to push when it comes to MOND and for whatever reason are emotionally attached to the idea that dark matter can't possibly be an explanation. Well, this is kind of strange. When you become wedded to particular ideas, you become emotionally engaged in defending or attacking, which shouldn't be the way that science proceeds. If we've got thousands of astronomers publishing hundreds of articles each week, and I'm not just making that number up, that is the number you get from the archive reports. You can ask ChatGPT as well. How many papers are published in astronomy every single week? It's somewhere between 200 and 300. We should expect this, just on the numbers, to have situations arise where observations are going to be published that, some of which are consistent with so-called modified Newtonian dynamics, and some of which are not consistent with modified Newtonian dynamics. That's just the way the numbers will fall. You're going to get a spread of data, not all of which is going to be accurate. After all, it's all just observations, and observations are difficult to interpret at times. Anyways, what is this MOND, modified Newtonian dynamics? And do these new observations lend credence to the idea that MOND is a good explanation? MOND is essentially an equation. That's it. An equation that seeks to modify Newtonian dynamics, which should be telling. After all, the theory of gravity is general relativity, not Newtonian dynamics. We've known for a long time that Newton's explanation of gravity as being a force has been shown to be incorrect, proven wrong by the Eddington experiment. However, you will also have cosmologists and scientists who are interested in defending modified Newtonian dynamics to say, well, it can also be used to replace general relativity. But the thing is, it is purely predictive. It's there only to predict the behaviour of bodies in orbit, like the stars in a spiral galaxy, or binary stars in a pair. It can't explain all of the dark matter phenomena. It can't explain, for example, why galaxy clusters move the way they do, or the galaxies in those galaxy clusters move the way they do. It can't account for that. We have a problem for which MOND is no actual solution because it's not an explanation. What MOND is instrumentalist. In other words, it exists purely to predict what is going to happen, but fails to explain why. What is the physical mechanism whereby MOND works? Gravity becomes weaker according to MOND, then general relativity says it should. Okay, but why? No explanation is given. This is what we call an ad hoc explanation. Explanation in scare quotes there because we have far more questions now than answers. We might solve, predicting the behaviour of many things where objects are deviating from general relativity, but we don't explain why they're deviating from general relativity. Do we have, as general relativity says, a curved space-time governed by a tensor equation or not? Why is space-time behaving in the way that MOND says it does? This is rather like asserting the prevailing view, general relativity, holds everywhere at all times except in those places where there appears to be a problem, in which case MOND holds, but doesn't explain why. Better to say, we just can't explain these observations right now. We don't know what it is, but according to the prevailing view, the reason why objects orbit at the rate that they do is because of the mass of those objects. The prevailing view predicts there should be more mass there, so we're looking for the mass. So we'll call it dark matter. It could always be the case that our theory of gravity is wrong, yes, but the new theory of gravity is not MOND. It's just an instrumentalist ad hoc prediction. It's not explanatory because it doesn't tell us anything about what really exists and why and how it behaves. Is it space-time and its curvature that is being changed by this MOND thing? Or is it a force in the way that Newton explained? And does that act instantaneously? So these observations of this binary star system are not evidence for MOND, even if consistent with it. Certain other studies are not evidence against MOND. After all, what can that mean? Evidence against what theory? An equation? All we have here are a set of problems, problematic observations that don't seem to fit with what the existing explanation predicts. Well, okay, that's science. I'd say MOND is itself also a problem, exacerbating things, not making things any simpler. Some studies have breathlessly claimed that their data support MOND at the 10 sigma level. Others say they rule it out at the 16 sigma level of confidence. By the way, 5 or 6 sigma confidence is the highest, 99.9999%. Sure that we're correct, or sure that it is this thing and not something else. So at the moment they've got two competing teams of people, both claiming super high degrees of confidence that MOND is correct on the one hand and incorrect on the other. It's all a big mess. It's a problem. The whole thing, not just MOND, dark matter remains a big problem. And quoting, therefore, statistical confidence levels for and against explanations that aren't explanations but ad hoc instrumentalist equations won't change that. It won't fix the problem with general relativity, if there is one, or those observations of galaxies rotating too fast. We need to know why, not just that they will rotate at this particular velocity or not. So, if I haven't laboured the point enough now, what we've got at the moment with respect to dark matter are anomalous observations and an otherwise good explanation, general relativity. Problems are bound to arise when we observe the universe. That's how science, and astronomy in particular, works. Almost all observations ever made anywhere in astronomy are consistent with general relativity. Indeed, not just consistent with, explained by general relativity. But some smaller number are problematic. Why? Experimental error? Experimental systematic error? Misinterpretation of the data by the community of astronomers? Something else? A false theory of gravitation, perhaps? Pointing to a new explanation, not merely an ad hoc predictive equation. Perhaps it's got something to do with the large-scale interference between Everettian universes. I don't know. No one does. But we should expect these situations to arise, problems with existing theories. What is not open to us at the moment is to move beyond we don't know. There's no point saying one believes in MOND, modified Newtonian dynamics, or not. That's utterly irrelevant. It doesn't matter if you believe in it. It doesn't matter if you're a physics professor who believes in MOND. That lends no credence to whether or not MOND is correct. Is MOND objectively a good explanation? It only seems to account, insofar as account is the right word to use here, for the rotation curves of galaxies. But that's not the only reason we think in terms of a problem here. As I say, whole galaxy clusters do not behave as we expect given the luminous mass within them. And by the way, all matter is luminous, by which I mean it has some temperature that some telescope can detect the wavelengths thereof. So we can see all the matter. This is the problem with this dark matter thing. If there's matter out there, it's matter that is not emitting light at any wavelength, which is really, really unusual. But we can't rule that out. We don't know yet. This is why we say, again, dark matter is the name of a problem. It could be that. It could be something else, more exotic still. MOND doesn't account for the motion of galaxy clusters or any other problem that dark matter seems to raise. What is gravity according to MOND? Is it a force, as Newton's theory says, or the curvature of space-time, as Einstein's theory says, denying the existence of a force? Well, MOND doesn't say that it's either. It's completely silent on that. It's not a theory of that kind. It's not going to explain gravity and doesn't purport to. Completely silent on that. It's just an instrumentalist equation. Insofar as science is a thing that explains the world, only a theoretical physicist could get away with that kind of thing. We're not going to explain gravity. We're silent on that. We're just going to tell you what happens next, perhaps in some situations, but not why exactly. Any reasonably competent fishermen can tell you when high tide will be tomorrow because they can look up a chart. Perhaps they can even recall it from memory. Perhaps they can give you a set of equations expressed in terms of trigonometric ratios, something like this, without being able to say why any of it works or ever referring to the moon or to gravity. I guess according to the MOND philosophy of science, this would make a fisherman a theoretical physicist of a kind as well. So this kind of equation, the one that I'm putting up on the screen now for tidal harmonics, it predicts what happens when the tide is going to be, or rather when the water level is going to be at a particular height. So you can predict when the high tide is going to be and the low tide is going to be using this equation. Imagine you were someone who dared ask, why does any of this work? Does the sun have anything to do with this? Does the moon? Irrelevant question, you might be told. It does not matter why. It works. You need to feel satisfied with the equation. There's no explanation further needed here. But you insist you want the explanation. I don't understand. Where does the equation come from? How do tides work? Here, they work like this, and they just point you to the equation again. Okay, so, well, there you go. So you know when the water will be so high. But why is it that high and not higher? Because the equation says so. If that seems like a silly example, it is the argument that MOND is offering us, and its apologists as well. Perhaps MOND works in some narrow predictive sense. But for those of us who want mechanisms, the hows and the whys and the what exists of the world, it does not. It's completely unsatisfactory. We want more than mere predictions of that kind. We need meat on the bones. We need some new theory to tell us about some new things that exist and perhaps yet to be found, just like general relativity did with black holes and gravitational waves. What kind of phenomena of that kind does MOND bring to the table? Well, I leave it as an exercise to the listener to disappoint themselves with the answers. Story number 2. The world's largest and longest ongoing experiment into fusion power is making some waves again, but for the wrong reasons in the Scientific American. But, the Scientific American is swiftly becoming like the left-leaning gossip magazine of the scientific world. Nevertheless, they're reporting that the largest fusion project in the world is over budget, and the researchers there just aren't producing enough of the goods. Here's a telling paragraph. Let me just read from this. So they're talking about ITER, which is the acronym for International Thermonuclear Experimental Reactor. ITER also happens to mean the path in Latin. There we go. Anyway, the Scientific American article reads in part thus, quote, "The plans for Notre Dame and other Gothic cathedrals, for example, were of such grand scale and intricacy that, from their outset, everyone knew their creation would span generations. No one present at Notre Dame's beginnings assumed they'd live to see it finished. ITER's designers, however, did not initially hold such lofty expectations for the project. Instead, they fully believed they'd see it completed within a couple of decades. Yet the project is now entering its third generation of planning and construction, and its important experiments are at least another generation away. ITER has become the Gothic cathedral of our time, a beautiful but immensely complex structure that we pray will help us find salvation from our energy and climate woes." End quote. All very pessimistic. So we're told the researchers fully believed they'd have solved all these intricate physics problems within some decades. Well, it should be the case that the investors shouldn't have cared what they believed. Again, science is not about belief or confidence, but creating theories and testing them, correcting errors, and the whole process is completely unpredictable. We have to escape this mindset of looking at scientific research as some kind of return on investment in the main. If we make it big, then we do make it really big. But failure is the default mode. Things go wrong. We know fusion is possible. Countless trillions of stars manage it every day without thinking once, let alone twice, about it. Nothing rules out doing it on Earth, as far as we know. But even if it does, We learn along the way about more powerful lasers and ways of keeping super high temperature plasma stable in magnetic fields, and who knows what all that leads to. Well, in fact, we can tell you some of the things that it leads to. Let's go to some of that, because it's well worth lingering over to see that it's not all wasted. All of this time and all of these billions spent on trying to get fusion, it's not like we don't learn anything along the road. So here's a little promotional pamphlet that, they produced to say, hey, we're not just wasting our time here, we're actually achieving some good stuff. Let's have a look at some of this. The so-called Spinoffs, which people will know from going to the moon, produced Spinoffs, technology that ended up having nothing to do with the moon, but having everything to do with day-to-day life and useful kinds of things you find in your own kitchen, like Teflon was discovered when trying to make a heat shield for re-entry purposes. So we've got military applications here. A new way of launching aircraft from aircraft carriers. There's one thing. Some people might not be happy with the fact that it's being put towards the military. I for one am. Industrial uses, such as the use of a kind of milliwave thermal analyzer, which helps improve the production of glass, metal and other industrial products, so we're told here. They've made progress on superconductivity. There's something very useful indeed. If they can figure out how to make wires from superconducting material, well, we're going to save a lot of money on electricity transmission. Lots of people are working on this. But hey, look, they're saying that they've made some progress. Indeed, they claim they've got the most compact high power density cable in the world. There we go. This one I really enjoyed reading about. The Miniature Integrated Nuclear Detection System. Let's just read a little bit about this one. The Miniature Integrated Nuclear Detection System was developed by engineers at the Plasma Physics Laboratory while working on decommissioning the tokamak fusion test reactor. So one of the previous generations of fusion reactor, when being decommissioned, they figured this out. After 9/11, its developers realised they had also come up with a technique to detect and identify nuclear materials in real time for homeland security operations, for transportation and site security. MONDS is used to scan moving vehicles, luggage, cargo vessels and the like for specific nuclear signatures associated with materials employed in radiological weapons. It's an anti-terrorism detection device. This is fantastic. What price can you put on something like that? I love this. This is great. Next, the compact syncocyclotron, which is used in cancer treatment to make valuable cancer treatment more available. Also developed here while trying to generate fusion power. Okay, so you fail in fusion power, but so far you're helping with anti-terrorism and you're treating cancer more effectively. Do I need to go on? I won't, but they go on with new kinds of semiconductors for computation and new kinds of polymers, and so it goes. I mean, the point here is, without me belabouring it too much, it's not all failure. We can't put a price on some of those things. In all these cases where they've found something that isn't fusion power, they've identified avenues to new solutions as they've encountered problems along the way. The path is a meandering one rather than a straight line between goal and achievement. The straight line never eventuates. You're always going to be distracted by this or that other problem along the way, and in solving that problem to reach your final destination, you make progress in places completely unexpected. Scientists engaging in things like fusion research are doing it because it's a passion project. For the most part. They're having fun with it. They're working hard, playing with ideas and concepts. Now, there are other interests at play with things like fusion power, just as there are with quantum computers. The desire to be first and win big and copyright and all of that stuff. But science, and often scientists, don't care quite so much about that. Yes, they want to be paid and deserve to be paid well, but if they wanted to be billionaires, they'd have different personalities and interests and problem situations. But they don't. They do what they want. And if you gave them $1 billion because they say they are interested in working on fusion, they'll continue working on fusion with that $1 billion rather than going and doing something else. They're going to take the money because, hey, they're working on fusion. That's what they're doing. Whether they've got $1 million or barely enough to survive or $1 billion, they're working on fusion. And they expect to fail. But they'll tell you that they hope that they won't, and here's all the reasons why they expect the thing to succeed. That's their area of expertise. They're hoping to succeed, they expect to succeed, because why would they be engaged in something where they expect to fail? They won't. They wouldn't be so passionate and having fun trying to solve this stuff. Okay, so some might make a spurious promise now and again, and they shouldn't. But if you're an investor, then it's incumbent upon you to understand this part of the philosophy or sociology of science. We can't predict the growth of knowledge. Fusion physicists, experts in their field, are no better than anyone else at predicting what will be discovered tomorrow in their own field. They are only experts in what is already known, not what is yet to be discovered. So you can ignore confidence and bravado. Invest in people, not promises. Promises are not proof. But people are problem solvers. You won't be so disappointed investing while using this heuristic when applied to pure science because you won't expect that the solution is just around the corner. You, like the scientists, will merely hope for progress of some kind anywhere at all. One possibility here is, yes, solving fusion power and having it ubiquitous across the world, solving all of our energy problems. Or finding the universal quantum computer and building it, so that we've all got a desktop version. Or the universal vaccine against all viruses, or whatever it is. But along the way, you're going to discover other things, even if you don't reach your goal. Don't believe promises. Just invest in people. Story 3. Really, 3 mini-stories in one. What's the James Webb Space Telescope been up to over the last few months? Well, I'm just picking 3 stories at random. It's been doing a lot of interesting stuff. First story here is about NASA's Webb proves galaxies transformed the early universe. Better to say, as the headline writer, NASA's Webb helps provide evidence to explain galaxies transformed the early universe. So here we have the Popperian view of problem, evidence, solution. The problem here was that after the Big Bang, the entire universe was extremely hot. It cooled, some initial stars and galaxies formed, and the rest of the intergalactic material, the clouds of material that were left out there, cooled to such a point that, well, just like fog on a cold wintry morning, it becomes impenetrable, difficult to see through, impossible to see through, opaque even, and that was the early universe. What happened then was so-called reionization. The cold material became transparent and it could be seen through. The light could move through that material. That was the problem. Why did this reionization occur? Well, it says here that new data from NASA's James Webb Space Telescope has pinpointed the reason. The galaxy's stars emitted enough light and heat to ionize the gas around them, clearing our collective view over hundreds of millions of years. And so this was the solution. This reionization happened because of these early stars and early galaxies heating up the fog and making it transparent. This is why reionization happened. Story 2. Just doing a quick set of stories here. Webb maps and finds traces of water in an ultra-hot gas giant's atmosphere. So this is one of these exoplanet systems, and one of these exoplanets, 400 light years away, was discovered originally in 2009, WASP 18b. It's a huge hot gas giant, 10 times more massive than Jupiter. One of the reasons that it can be seen, actually, because that's the kind of size planet that is easier to observe, of course. The discovery, water vapor in the atmosphere of WASP 18b. And this was figured out because you can do spectroscopy of this planet as it orbits its star. The star sends out light that can pass through the atmosphere, which can then be analysed by the James Webb Space Telescope. So we can detect chemicals on planets 400 light years away. This is astonishing stuff that the James Webb Space Telescope can do, and here's another example of where water has been found well beyond our solar system on another planet. Gas giant, admittedly. And also, speaking about water, something closer to home, Webb maps surprisingly large plume jetting from Saturn's moon Enceladus. A water vapor plume from Saturn's moon Enceladus spanning more than 6,000 miles. The distance from Los Angeles to Buenos Aires, has been detected by researchers using NASA's James Webb Space Telescope. Not only is this the first time such a water emission has been seen over such an expansive distance, but Webb is also giving scientists a direct look for the first time at how this emission feeds the water supply for the entire system of Saturn and its rings. So it's like a volcano erupting water vapor, and this in part is feeding Saturn's own rings. And so the rings are out there, also made of ices and rocks. And where does the ice come from? In part, volcanoes on Enceladus, spewing water vapor out into the orbit of the rings. They say Enceladus is an ocean world about 4% the size of Earth. It's only 313 miles across. But one of the most exciting targets in the solar system, the search for life beyond the Earth. Because between the moon's icy outer crust, so it's got a solid crust of ice, and its rocky core is a reservoir of salty water. So there's energy there, keeping from the core of the moon, keeping the water liquid beneath a protective shield of ice. Possibly important because Saturn's going to be putting out a lot of radiation. So who knows if there's life forms down there. Important to get a sample of this if one day we can go there, because maybe it's a kind of life that is completely separate to the kind of life that evolved here on Earth. Sure, it might only be bacterial, but it'll be very interesting to see if it has a common ancestor with the life that's here on Earth, or if it's completely different. That would be fascinating. So it's very interesting to know that, well, we've got rich chemicals out there. We've got a moon made of the same sort of stuff that everything else in the solar system is made out of. In other words, rocky core. And you've got heaps of water, and you've got an energy source. Everything, apparently, that you need if you want to get life going. Who knows if there are fish out there? I doubt it, but I wouldn't be surprised if there's not something akin to bacteria out there. We're yet to find out. As it is, we don't know yet. It's just an interesting, tantalizing possibility. That'll do for today. Rather narrowly focused on physics, I understand, but that's what I do. Until next time, check out part 3 of my discussion of the fabric of reality, chapter 9, quantum computers, where we go over again and into more depth about our discussion of the discrete and the continuous, among other things, given our understanding of physics and in particular Everettian quantum theory. Until next time, bye-bye.